Okay, I'm going to make another video on what we talked about last class about impulses and impulse response. And this is from note set 12. And I'm going to go through this as more of a summary rather than a really in-depth derivation of things so that we can kind of put the important bits together. So first off, we know that an impulse, which we call f hat, this is an impulse. It's equal to f delta t. It's a force acting over some interval of time. And what we learned from class is that this is also equal to the change in momentum. So this is the momentum change. And we know that momentum is going to be something like mv, at some instant in time, minus mv at some other instance in time that happened before a collision, let's say. So what we assume is that the initial state of the system is 0, so that goes away. And what we end up getting is this velocity that we will describe as being the initial velocity of our system. So what we say is that f delta t is equal to m v naught. This is the initial velocity of the system due to the impulse or to the impact that occurs. So we end up getting that v naught is equal to f delta t over m, and f delta t we know is f hat. That's the first important point, that our initial velocity can be related to the impulse that caused the system to move. Now, let's look at any system, and the one that we did in class was an underdamped system. Where basically we have an equation like mx double dot plus cx dot from kx is equal to 0, except now what I'm going to do is assign initial conditions where the initial position, let me write this out so that it's more like the note. So x of 0 is x naught, and we say that's equal to 0 for these types of problems. We say the initial position of the system is 0 when it's exposed to the impulse. And x dot of 0 is the initial velocity, which we know is f hat over m, the impulse over the mass. So if we have an underdamped system, we go through all the math for this. That was the whole assumed solution of something like a e to the lambda t, and you find lambdas. We ended up doing the quadratic equation to find those lambdas and then substituting them back in. And depending on what the lambda values were, that's what determined the response of a system, if it's underdamped, overdamped, or critically damped. So that response ended up being something like a e to the minus zeta omega nt times sine of omega dt plus phi. And we can see that this is the decaying portion because it's damped. So as time goes on, the motion will get smaller. And then we have this guy, which is the oscillating portion, which only exists because of the fact that we're underdamped. So I'm going to look back at my notes. I don't remember these equations off the top of my head, but we can find the amplitude and the phase for these guys. Where is it? And since we know the amplitude and the phase, we can go ahead and find what they are with our given initial velocity. So the amplitude, and this is derived in an earlier note set, is something like v naught plus zeta omega n x naught squared plus x naught omega d squared, all that divided by omega d, and our phase ends up being the arctangent of x naught omega d, all that over v naught plus x naught zeta omega n. So those are our amplitude and our phase that we've derived in note set 5, I think, for an underdamped system. And we were given for this type of problem what the initial conditions are. So we know that x naught is 0. So if x naught is 0, that means that we lose this term, we lose this term, and we lose that term, which basically means that that becomes a 0 on the top, which automatically tells us that our phase is 0. So we got that. Our amplitude with the x naughts gone just becomes the square root of v naught squared, which means that they're going to cancel the square and the square root, which just leaves us with a v naught and then the denominator omega d. Because we're assuming that the initial position is 0. So with that in mind, x of t, I'll just write it again, a e to the minus zeta omega n t, omega dt plus phi. Substituting in those values now, we end up getting x of t, and our amplitude again, I think was v naught over omega d. Yep, v naught over omega d, e to the minus zeta omega nt times sine of omega dt, and the phase was 0. So that would be our underdamped response regardless of an impulse. This is just in general. If I have some initial velocity, that's what the response would be with no initial position. But for the impulse, we know that our v naught is equal to the impulse over m. That's what we found before. So if I substitute that in, this is going to be due to the impulse now. That's going to be f hat over m omega d, e to the minus 8 omega nt, and omega dt. So this basically says if I apply an impulse of 1,000 Newton seconds, that's my f hat, I can find what x of t is for any system, that's underdamped. So what we care about, though, is a very general form of this. Like, let's assume f hat is equal to 1. Which, if we come back to, and I didn't talk about this in this video, but we talked about it a little bit in class, is that if I have some impulse, let's say I center it at 0, the area under the graph is equal to f hat, which means that for this specific case, it'd be equal to 1. Remember, this is t, and this is f of t. That specific case where our area is equal to 1, and again, this is a function of time. Something is sitting still with respect to time, and then at t equals 0, bam, something hits it, and then nothing else happens after that except the vibration, but there's no more forces acting. This specific impulse is called the Dirac-Delta function. And that is given by delta of t. Let me see if I can move this around without this getting stupid, because sometimes this gets really complicated. Yep, like that. So annoying. Just let me move it. So the point is, though, that if I integrate this, the integral of a function with respect to time is the impulse, that's the area under the curve. Specifically for the Dirac-Delta function, f hat for Dirac-Delta, that's the integral from -infinity to infinity of delta of t dt. That is equal to 1. I just put Dirac-Delta to show we're plugging in delta, but we would just leave that as f hat. So f hat is equal to 1 specifically for that case. And because the Dirac-Delta function is more of a foundational thing, it's something that mathematicians have defined and that engineers use as kind of a standard, we will build off of that. So let's rewrite our underdamped response is f hat times 1 over m omega d, the complex or the exponential times sine of omega dt. And what we see is if f hat is equal to 1, meaning we used Dirac-Delta to create the impulse, that means x of t would end up being, if f hat is 1, just that other term, the leftover stuff. And this is what we call the impulse response. Impulse response function. So the impulse response function is the concept of that if I apply an impulse that has a value of 1, meaning that we use a Dirac-Delta, this is how the system would respond. It would oscillate, at some sine omega dt, and then it would be decaying over time due to zeta. So it might look something like this, kind of like we've seen in earlier node sets, where it oscillates up and down and then eventually decays. That's what we call the impulse response. So I hit it, it will vibrate a little bit, then it'll just decay for an underdamped system like this. Hopefully that makes sense. So with that in mind, let me erase this a little bit. This is the impulse response function. We call this the letter H. This is the impulse response function. We can see up here that if f hat is 1, we just get this. That is my impulse response function. So I'll say that my position is going to be based on how strong my impulse is, but I'm going to multiply that by the impulse response function. So a way to think about that conceptually is that if I just apply an impulse of 1, which is just our normal impulse response function, I get this type of thing. If I apply an impulse of 10, that's going to be the same exact response, except now I'm going to have a much greater amplitude. I might have something like this, in red, where it's the same exact response, the same frequency, same type of damping, but because of the fact that we are doing it with more oomph, like more, I don't want to say, it is technically with like more force, but, we're applying a much greater impulse, that's going to cause our impulse response to be amplified. So we end up with a different magnitude or a different amplitude of our response because of that. Hopefully that would make sense. So that's our general impulse response function. And the benefit of doing this, ultimately, let me see if I start going into this. Yeah, I do, okay. The general idea of this is that if I have some arbitrary function, I don't know what it is, but something like this that happens, maybe it continues on forever, I can model every single point here as an impulse. So this is an impulse, and then directly afterwards, is another impulse. And there are an infinite amount of impulses that are active. So there's an infinite amount of impulses that occur over very, very, very small intervals of time, basically 0, but very small delta t. Infinite impulses that each contribute a response. So one impulse is going to cause it to vibrate. The next impulse is going to cause it to vibrate more, possibly. The next impulse, and they just keep acting, and their contributions keep summing. So what we want to do is find what the contribution from one impulse is, where we say that that one impulse is centered at some time tau, and then continuously add them up. So I'll say, and this is f of t here, that the displacement, which I think I called delta x in notes, I don't think I called it delta x in class, but basically it is the small contribution that impacts the displacement for a given impulse. I'll say that given impulse is I. That's going to be the force at that t. you know, and that tau up here. I'll just call it t sub I for now, because it depends on what impulse I'm looking at. If I'm looking at an impulse over here, that impulse is at a completely new time. This is a different t, you know, and so on and so forth. There's a bunch of different t's depending on which impulse we're looking at. So this change of position is going to be the impulse multiplied by the impulse response function. But the impulse response function, if we come back to it, this is our impulse response function here. This is assuming that we have applied the impulse at t equals 0. Basically, when I hit it at the beginning of the problem, t equals 0, we get some response afterwards. But if I apply it later in time, maybe 3 seconds or 4 seconds or whatever, the system isn't going to move until it's exposed to that impulse. And then from that point on, it'll decay at this same impulse response function. But we have to take that into account. The way that we do that is by shifting the location of the impulse to the right, by subtracting out what value of time we're at. So for example, this was h of t. That means impulse at t equals 0. If I do h of t minus 1, that means the impulse occurred at t equals 1. H of t minus 3, this was at t equals 3, and so on. I can do this for any time, and that's why I say it's h of t minus ti. This is at t is equal to ti, which changes depending which impulse I'm looking at. If I'm looking at the first one or the last one or whatever, the location of that impulse is going to impact the impulse response function. Another way of thinking about this is that if I apply an impulse, you know, let's say here, there's this impulse right at the front of the curve. This impulse over here won't impact the response because it hasn't happened yet. Like I hit the machine or something with an impulse, this guy here. You know, I find what that contribution of position is using this equation. But then it will be completely unbeknownst to it that this impulse is coming. So we have to keep shifting the impulse response function in order to take into account the fact that these impulses are occurring later and their contributions cannot be taken into account until those impulses occur, which is kind of confusing. So I hope I said that clear enough. If not, go back and rewind and then come talk to me, you know, if you have questions. But this is the contribution from one impulse. What I want to do is get all the impulses. So what we'll do is we will say that our total response is the summation of all those impulses. So delta x. We'll do that from I equals to 1 to, you know, how many impulses we have. We rewrite this in terms of what our definition of delta x was. That's going to be the force at ti times h of t minus ti. And we know that our force, actually, let me double check something real quick. This is the impulse. Sorry, that's the impulse. This is the impulse. The reason it's the impulse is we come back here, we showed that f hat's in the front of the impulse response function. So it's the impulse that is in the front. With that impulse there, we can substitute in and say this is the force times the amount of time that it occurs over. So I'll just write this first, and I'll put the amount of time over here, which we'll say is the ti, which is a differential of time that occurs at that position I of that impulse. Now, if we let, you know, that amount of time go to 0, basically meaning we're having more and more impulses, an infinite amount of impulses, that will convert this to an integral. Or instead of integrating from, you know, t equals I, ti is equal to 1 to tn or something, we'll just integrate across the entire time, which will be from 0 to whatever time we care about. You know, maybe there is a string of impulses that are constantly occurring. Maybe I only care about what the position is due to the first 4 of them. So I'll just integrate those 4 up to, amount of time that takes. So this is going to end up being f, of ti, h of t minus ti, dt ti. But because we're not doing a summation anymore, we don't need to include the subscript I. That doesn't really make sense if we're not in a summation. Instead, what we'll do is we will rewrite this as a shifted variable tau. This is our convolution integral that is equal to our response. So the general benefit of this is that if we have any arbitrary response, let's break it down into steps real quick. I'll just recap this. So let's say I hit it with a hammer. So I hit it with a hammer. That allows us to measure our impulse response. And the way I drew it would really be this: h of t minus tau. For this distance is tau. So we can measure how it deflects, because remember, h of t, this has units of meters, because of the fact that it's the displacement of the mass due to that impulse of 1. Once we have the impulse response function, that's what we just captured, we then can use that for anything we want. This is some random f of t or whatever, and I can go ahead and convolve those two, which is what that integral was. I can say that x of t is this random function f of t convolved with h of t, and that's what gives us our integral f of tau minus tau d tau. That's the benefit of doing this, is that if we were to sum up the contribution from every single impulse and ensure that we're shifting our impulse response function with respect to this dummy variable tau, that will allow us to see the total sum of the individual contributions from each individual impulse. So this impulse here, that's going to cause some response. The next impulse, that's going to cause some response. The next impulse, they're going to all keep going on top of each other because of superposition. They keep adding and adding. So by summing them, we will find the total effect that they each individually have on the system and the resulting displacement. Hopefully that helps.